Okay, so I don't really have any notes per se on the Simulink. I just used what was on Canvas. But I thought I would record myself getting through this, through the first exam that we did, like step by step to explain my thinking, because hopefully that makes it easier for you to understand how to use it. So yeah. Step one is open Matlab, of course. So bear with me here, because I did not plan like a script or something, so I'm just winging it. Alright, here we go. So to open Matlab or Simulink, you can just type Simulink into the command window, and it should open. Yep, perfect. Let's go here. Let me make a new folder for all this. Let's see, first exam tutorial. Why not? So here we're gonna create a new live script. Why not? Exam 1, 2 tutorial. Okay, so first things first, you always want to clear everything, and yeah, there we go. Okay, Simulink, let me, this is a new version of Simulink. Well, okay, no. So let's just do this. So exercise 1, it was the only exercise actually, was to basically model this pendulum here, because it behaves as a second order system. So we are given some information. The first bit of information here is that when you only use very small angles on the pendulum, it doesn't really specify which ones. We just have to go with this for small angles, and then for, you know, the more general, the more complete thing is this. So let's write this down. So we have second derivative plus GL is 0. Let me write that down here. So we are given that the second derivative, let me just do it shorthand to not waste too much time, plus GL slash theta equals 0. So this is 1 for small angles, and then we have that m squared BL MGL. Okay. So we have ML squared slash theta second derivative BL theta first one plus MGL in theta equals 0. Okay, there we go. So this is the complete model. Okay, so now move this to back. No, here, question 1a. Create a Simulink model to solve the nonlinear equation. The calculation of a sinus is done with the block trig function, which can be found in math operators. Okay, so here they tell you where to find the actual block that we need to use, this one. Use the following settings. Okay, so here, let's create the model. Hey, good job, Simulink. Why are you like this? Okay, so here we've got a blank model. Let's save it as save as first exam tutorial. I don't know. First exam models. Let's just say exam models then. Happy. Hey, there we go. Okay, so question 1a. We are told that, let's see, m is 1.5. So m is 1.5. Do they give us units? No. Length 3b 0.1. L is 3 and b is 0.1. The reason I am doing it here in Matlab is because in Matlab, as you know, you can use variables. So you can change the variable here, and then if you use the variable inside of Simulink, whatever you do here within Matlab will be applied to here. So you don't need to go back and forth into the model once you've finished it to, do whatever changes you need to do. You can just do it from here, which is a lot easier. So make sure that all parameters, including start angle, can be set from within Matlab. Okay, they wanted to do that anyway. Yes, with variation. Okay, so that's for later. Here, this was a very important note. So it says that Simulink works with radians. However, we are gonna be inputting numbers in degrees, and whatever output that we show should also be in degrees, which means we need to convert back and forth. So do keep this in mind. So let's be nice and organized. So given variables, we know that g, the gravitational constant, is 9.81 more or less. ms minus 2. Let me add a few more things, because I also want to be able to change like the simulation length, so for how long the simulation actually runs. So let's say t stop small for the small angle thing. I don't know, I think the default is 20, right? Like 20 seconds. So let's do this, and then let's say t stop full is also 20 for now. We need a starting value, so theta 0 will be, I don't know, something for now. I think. So this will be something, and this will be in degrees, but we need to convert this to radians, remember? So let's say theta 0 rad will be pi over 180 times theta 0. Yep. So this is now in radians. Okay, there we go. So first, I always well, let's start with a small angle approximation because that's probably a lot easier. So we have a second derivative. Okay, so we have an integrator. Here, an integrator. You can double left click on an empty area of the board here to bring up that search function and just look it up. So let's say this is theta dash dash, or you know what, let's leave it blank for now. So then we need another one. You can just Control-C, Control-V to paste. We connect this. So this will be theta dash dash, which means this is now just theta dash, and this comes out as just theta. The way you label these lines here is by double left clicking. So yeah, let's do. Okay, we need to take. We need to multiply normal theta by g over L. So we need to get a gain block. This multiplies, and I'm gonna rotate it to keep it nice and clean. So this should be g divided by g. Wait, I need to. Okay, so to load this space into your workspace, you either need to run it once or press F5. So there we go, it is now loaded into the workspace. So now here, when I type G, it should show me G. Yes, there we go. Over L. So L, yeah. So there we go. Because you need to take a screenshot of this for the exam, you should expand this thing so that you can actually see what specifically is the gain. Because otherwise you will lose points for that. Well, okay, so we can say that the second derivative is equal to minus g over L theta, right? You just move this to the other side. So if here, this line here is theta, that should be equal to minus g over L times normal theta, right? And then from here, if you hold down right click, you can like split the path. And here is where we're going to take the output. So let's do workspace, tool workspace. So tool workspace will send stuff out from Simulink to your workspace. So let me, what are we gonna call this? Small. Sure, why not? Okay, so this is the thing for the small angle. So if you imagine you move this to the other side, you get theta dash dash is equal to minus g over L times theta. So okay, we get theta dash dash is equal to minus gl times theta. So good. And what we want to like measure or plot, what we care about is theta itself, which is why we take an output from theta to the workspace. So this is our first model. And now let's make another one. Let's start with the second derivative here. So we have We need an integrator. Oh wait, no, we still need to set initial conditions, sorry. So here, initial condition for this thing will be theta 0 rad. There we go, okay. This thing also theta 0 rad. Okay. Is there something else? No, I don't think so. Yeah. Okay, so we have the initial conditions, we have the gain, and we've got the output. Sure, let me just... you know what, let me do this in two separate things. So here in the stop time, remember we had a variable for that called t stop small. Okay, so I'm gonna save this and we're gonna rename this. Name exam small. Okay, perfect. That should, yeah. Okay, perfect. And now we're gonna make a new one for the other one. So first, let's save as. We're gonna call it exam big. Save. Okay, so let's see. So we have here mg ml squared. Okay, so let's put a gain. This is gonna be m or m times g times l. No, it's ml squared. Times l squared. That's good. I don't trust this though, so let's just do this. Nope. There we go. So now you can see what it is. Yeah. Then let's add an integrator. Boop. So this is 0 rad. Okay, we can also do stop. Keep stop. Full, did we call it? Yes. Stop full. So okay, so this is ml squared theta dash dash, which means let's copy this integrator. So we should have that, yes. This is theta dash, except we need to multiply that by something, so let's get a gain. So we multiply this by BL. Okay. So let's rotate this. Dash. So times L. Okay. Okay, that's good. And then we need to get sine of theta, right? So sine. This is the block that they told us to use, so we know it's good. Let's connect it to here, because this is theta. I do recommend that you label your things, because like that you can read what's going on. So with this we need to multiply by MGL. So M times T times L. Perfect. Okay. And here again, you want to basically move everything but the highest order derivative to the right side, so you would get ml squared theta dash dash is equal to minus bl theta dash minus mgl sin of theta. So we need to get to minus, so sum. So this will be, no, this will be minus minus. Yep, perfect. So, this is mgl sin theta. And this is sin theta. And this is BL theta dash. You go into here. And you go into there. Yeah. So there we go, and obviously we care about theta, so we take output from this workspace, and let's stay consistent by calling this big. Okay, perfect. Do I need to change other stuff? No. Sine? No. Yes. To get your signal to be more clear, you can go into model settings, then data import export, additional parameters, refine, and you can increase this to like 10. So let me do that for this one as well. Model settings, data import, additional, refine 10. So, and you should also save. Okay, there we go. So you take screenshot of this is your big model, and you take screenshot of this, and this is your small model. So that's the model complete. And here we have all the parameters. We have like the constant, well, we have the gravitational acceleration. We have simulation durations, and we have initial conditions, or condition. Let's do that. Okay, there we go. So that is question 1A. Question 1A is to make this model and this model, and you need to be able to control those variables from inside Matlab. So we have successfully done that. Let's do 1B now. Okay, so move it to back. Okay, so 1B. Generate a time response with a start angle of 30 degrees and compare the result with the response of a small angle approximation. Copy, paste, and output of the scope that shows both responses in the same figure. Okay. Okay. ensure that the generated output is sufficiently smooth. So this we already took care of by increasing the refine factor, and sufficient time to get 5 swings. Well, we can see if we do that, and if it's needed, you know, we can increase the simulation duration or decrease it with this value here. So that's not an issue. With standard settings on some okay, so here they tell you to add the refinement factor. Okay, whatever, we already did that, so this is the only thing, and we need to make sure there's at least 5 swings. So let's do that. Okay, so we need to we need to load the Simulink files into Matlab here, so that, you know, when we run this Matlab script, it actually runs the simulation. So let's go ahead and do that. Let's see. Running. Alright, let's put here. Running simulations. Let's say small angle will be sim. So for you can name it whatever, but as we have two, I'm gonna give it 2 different things. And then here you have the file names, because I put them in the same folder, they appear here. So we're gonna go exam small for the small angle, and then you can do the same for the full. So let's say full angle is sim exam big. Perfect. Okay, so this will run the simulation. Then we need to convert back to degrees, because if you remember here, we are doing stuff in radians and our theta is in radians, so we need to you know, convert the stuff. So first we need to get theta from sims. So small theta, what am I doing? Small theta will be oh wait, no, this is gonna be in radians. So small theta radians is gonna be, kind of forget how this works honestly, so let me just run it. Wait 20 seconds. Okay, so here we now have both simulations, so let me open this one. Okay, we've got time series and T out. Okay, so perfect. Okay, so we know that small is our theta. Okay, got it. Yes, I remember now. So small theta will be a small angle, right? This is our simulation. That's the name of this simulation here. Dot data, right? We want the data, and we need to convert this back to degrees. So we do 180 over pi, voila, and then we get big theta rad. You know what? Let me do the conversion after. Is equal to call it full angle dot data. So see if we don't get any errors. Shit. Okay, what did I do wrong? Oh, yeah, okay, wait, this is the time series, so we're gonna get small, right? And this one was big. Yeah, okay, so small, so if we open small theta, now here we have a data and a time stream. So, okay, there we go, that, I was skipping a step. Okay, so now we convert back to degrees, so we do, yeah, I mean, I'm too lazy to type, but basically you do, we just want the data though. Data, right, because converting the time to degrees doesn't make sense. So there we go. Should give us big theta degrees and small theta degrees here. There we go, beautiful. Okay, and now we need to plot the results, right? That shows both responses in the same figure. Okay, so for this I'm gonna use a subplot because we need two plots in the same figure. So the way I'm gonna do that is with Matlab subplot. So let's do plotting figure hold on subplot. We want 2 rows, 1 column, slot 1. Yep. Okay, and then here we can plot, let's do the small one first. Small theta degrees in the x. In the x? No. In the y. Okay, so this will be the y. And here we need small angle, small theta rad dot time in the x, and then the actual thing on the right. And then just to be good boys, we are gonna, be proper and give it a title. I don't know, small angle approximation. With 30 degrees. 13. Take. X label will be no, time in seconds, I guess. And the Y label will be theta in degrees. Okay, and then here we're gonna make the second subplot. So it's, here you can see Matlab is already suggesting me to do this. At the exam, obviously you won't have this suggestion, but it's basically to copy this. It's just that you change the small theta to the big theta, right? Because you want the plot of the second thing. And that's it. Hold off, and that should be the figure. Let's see. Okay, so this is obviously way too long of a simulation. So let's cut it in half. This is the full one, so let's say t stop full 10. So you see now it stops at 10, but it's still quite a lot, so I don't know, 6. So that's a nice thing about, adding the stop time within Matlab, because otherwise we would have to go back into Simulink and change the stop time and run it, and whereas here we can just do this. And what's nice is you can see that it does indeed start at 30 degrees and then swings back and forth. Okay, you know what's great? I'm doing 4. Yeah, okay, great. So that's it for question B. 1C. So yeah, that's question B. We know it's smooth enough because we already have changed the refine, and Obviously we adjusted the thing, so this already has more than 5 swings, so we don't need to adjust that. But this one was way too long with 20 seconds, so we actually reduced it. So yeah. 1C, generate output of the scope to Matlab's workspace for a start angle of 30 degrees and write a Matlab script that can 1. Run a Simulink file and 2. Plot within Matlab the response and determines the height. Okay, so this we already did. So, right, because we ran the Simulink file through Matlab, so that's not a problem. We also plotted the response already, so that's fine. And 3 determines the height and the time of the first maximum. Okay, so for this, if you're doing this at home, you are gonna need the, like, what's it called, signals, control systems toolbox here, and the signal processing toolbox, because we are gonna use some functions from that. So you do need to have that installed. If you don't know if you have it installed, just type vir into the command window and it will tell you all the stuff that you have. These toolboxes will be installed on the Matlab that you'll be running, because Herbert also uses them in his example, so I feel like we're allowed to use them. So yeah. So for question 1C, you can copy this for part 1 and 2. And then for part C, the only thing we need to add actually is to determine the height and time of the first maximum. Okay, so for this, in the exam we had access to the workshop PDF, and there they literally have the code. I have it open on my other monitor, so we can just copy that code basically. So let's do small angle props. I don't know what you're suggesting, bro. So okay, let's call this YS and XS for small. Now is find peaks. So this is the function I was talking about. Find peaks basically finds the local maxima, which, you know, is kind of well, both maxima and minima, which is kind of convenient. So yx is equal to find peaks of small theta deg and small theta. Yeah, good type small theta rad time. So yeah, you need to put in the y and then the x, and then you get the thing. Yeah. Okay, perfect. Why is this yellow? I don't know. Okay, fine. I'll add a comma. So, okay, perfect. We now have XS and YS. Amazing. So, now that we've found the positions of all the peaks here in the small thingy, we need to find, what did they want? the height and time of the first maximum. Okay. So do you want this one here, more or less? Well, let's see if we get that one. MP equals. I'm literally just copying this from the workshop m.pdf that we had access to. So max ys minus theta 0 degrees. We're working in degrees now. Over theta 0. Is that correct? Because the max peak is the maximum minus the initial. Maximum minus the initial. Divided by initial minus infinity, which is 0, basically, right? The average. So I think this is good. So this would be small. I'm not gonna put the semicolon here so that it actually, you know, echoes into the void. Here. So like that later I can just, you know, take a screenshot of all the values here. So, well, you would have to take a screenshot for that. So TD small will be wait, let's make this nice. Printf small angle prox slash n. Yeah, okay, whatever, it's fine. TD so TD, so that's the time between the two peaks here. So we will do xs2, right, the second peak, minus xs1, the first peak. So this is the period, this is the peak, and then with this we can do the thing. So the zeta small is equal to square root of 1 over 1 plus pi divided by log of mp small. Which one is this? This is the log, this is the pi. So this one has to be squared. And then omega n small. Bro, why can I type? Omega n small is 2 times pi times 2 pi over td td small times square root of 1 minus theta small squared. Nope. Use of operator. Did I miss something? What has gone wrong here? Oh, I have times and divide. Okay. Yeah, so 2 pi divided by tt small times square root of 1 minus beta squared. Okay, this should be good now. And there we go. Yeah, and now we need to do the same for the big one. God damn it. You know what? No, copy this. Copy this. Full angle. Let's change this to F. So shift enter. God damn it. Shift. Okay, there we go. So let me just rename all this. MP for oh no, what did I do? No. Okay, there we go. So you basically just rename all the variables for all that. What did I call this? Big and big and oh no, there we go. That's 1C. Okay, so you copy all this Matlab code basically, and you paste it into here, and that's it. Yeah, I think I went quiet there for a second. But yeah, basically you did this. I literally just copied from the workshop _m PDF file that they gave us access to, and that's it. I am good. 1D, investigate how the natural frequency and the damping factor determined from the first peak change with the start angle in the range from 1 up to 90 degrees. One for the natural frequency and one for the damping factor. Okay, this is just plotting. Thank God, with a for loop. So analyzing starting angles. So they want to go from 1 to 90 degrees. So we're gonna make a for loop for I equals 1 to 90. Well, basically we just update this, run the simulation, and we want to plot the natural frequency as a function of starting angle. Okay, so we need to keep track of the starting angle. We're gonna use a for loop to basically go from 1 degree all the way to 90 degrees. starting angle, and then we're gonna plot the thing again. So first, let's reset the simulation duration. So let's do 20 so that it has enough time to settle. Then we need to update the starting angles. Let me. So update starting angle. So update the starting angle, theta 0 equals I. Okay, let's actually make a list of the starting angles. Starting angles equals blank. Or no, let's pre-allocate the space. Once 90. I want one row 90 columns, right? Right, this is how that works. Yeah. Yeah, perfect. Okay, so for we update the starting angle, we log the starting angle. Oh, what is all this? No, okay, let's okay, so, hey, starting angle. So starting angles I equals I. Perfect. Then we run the simulations. So yeah. Well, let's do small sweep so that we keep it separate. So small sweep and full sweep. Then we need to do this again. Okay, so we run the simulations, we get this thing. So this is small sweep now. This is small sweep. Yeah, sure. Let's do RS so that it doesn't mess with the other variables. You probably don't have to do this, but I'm always sort of paranoid that something will go wrong, and then I won't have so much fun. So I'm just keeping the names of the variables different, except of course the initial conditions, because these are the ones that the simulation actually uses, so we can't change the names of those. Okay, and then we need to calculate this again. God damn it. I mean, luckily we already did all the math for that. We just need to copy it into here, make it look nice and pretty. Voila. YSS. Let me rename all these things. Rename all this just to avoid issues because I'm a paranoid boy. That looks correct. We don't need this actually because I don't want it calling into the void every time, like every loop. So let's actually add colons here this time. Here, nope. Here. Here. Well, this needs to be S. And this needs to be RS. And this needs to be DS. And this needs to be RS. Okay. So, yeah. Perfect. Okay, perfect. And then we end. Oh wait, we also need to keep track of zeta and omega. Okay, so I need to keep track of that. So let's copy this. Let's call this omega n sweep and zeta big sweep. I forgot there's two of these. God damn it. Let me just copy this. Fuck. Okay, where the fuck was I? Yes, we need to log all this stupid bullshit. Okay, omega and big sweep. Well, okay, so this will store starting angles. This one will store small zeta. Oh no, small omega n. It's lovely, but I don't care. This one is to store the small zeta. This one is to store the full omega n, and this one is to store the full zeta. Okay, so once we've calculated here the small things, let's add it to the thing. So yeah, basically omega n small is equal to whatever this was, then the zeta for this iteration is whatever this was, and same for here. As I said, now of course we use the other things. And okay, and then we need to do some more plotting, so let me copy this. So this will be the first one, and we're just going to include the the big title, so let's say omega n as function of omega n and zeta as function of starting angle. Sure. Okay, so we're gonna plot. This should be the small one. So on the x we want starting angles, and on the y we want. Let's put omega first. Why not? So this is. Let's not put an x label for this one. And we're just gonna put omega n. And then here we're gonna put starting angles thick. And this one will be zeta, right? Let's copy this, place it into here, and this should be zeta now. So let's see if this works. Oh no. Oh no, what went wrong? No. Something has gone terribly wrong. God damn it. Why? Well, here I saw that I stored, I don't know if you can see, but after zeta and omega n, there is an indexing I. So basically, instead of having all these separate lists like I did this time, I just extracted each variable into a list every single loop. So I decided to also try that here to see if it changed anything. So right now I am gonna delete here the logging of the results. So first we add the indexing I and the two zeta and omega for both thingies, and then you need get rid of the logging because we don't have those lists anymore, in the hopes that this would actually do something. unfortunately, that was not the issue. The issue, it turned out, was that we had to use the first peak uh, for, yeah, to calculate this thing. So if you look at my MP function there, we're doing the same MP function as before, even though we should just be taking the maximum value. So yeah, that's basically it. Here I'm yeah, here I'm changing the variables because the lists that we had before don't exist anymore. Now we're just using the straight up variables from the for loop, so I had to change that in the plotting as well. And yeah. Now the issue here, yeah, I got an error with like using the power operator wrong. And that's because now zeta within the for loop becomes a list. So in the first loop, it's fine, but in the second loop, zeta now has two entries. So without doing matrix multiplication, Matlab throws an error. So you need to add the index indicator to zeta in the omega n line. But yeah, here I was just trying to figure out what was not working. So I added the indexing indicator here on line 91 before adding all these stops. So here I'm just looking in the workspace to see what happens. And here I am getting no error in the first loop of the whole code here. So, okay, I didn't really know what was going on. I just go through the second loop again and I get the error. So, okay, now I know that it's something with the full angle. I should have realized by now that it was the zeta thing because I corrected it in the small angle, but not the full angle. But yeah, here I'm just testing it basically to see if I can actually figure out how to do something. So yeah, here we're on the MP. Obviously, no issues with that. Here we move on to the next thing. I don't know what I'm checking here. Oh, I'm probably checking the values of the thing. Yeah, I don't see anything wrong right now, so I just I mean I was like more than 1.5 hours into the recording. So I was pretty tired. I couldn't really see it like at first glance. But yeah, eventually I did figure it out. So I'm probably just gonna cut now to that point. But yeah, I just wanted to explain what sort of debugging steps I took. Oh, yeah, well, here I noticed. Okay, there we go. I added the I. Okay, yeah. So now it works fine. Or not. Oh wait, no, yeah, it didn't. No, this is because Matlab is stupid. No, if you make the change, it's still running like the old code, so you need to stop it and then run it again. And as you can see, I didn't get an error now. So yeah, here I'm just pointing out that the issue was with the zeta because zeta is now a list or an array, I guess. So as we don't want to square the entire array, we just want the value for this loop. You need to add the index indicator, but that's it. It's a small mistake, but yeah, it's very annoying to catch stuff like that. So yeah. Okay, so once I had solved that problem, I ran, the code again. But unfortunately, um, yeah, the things I just did was change the way we store the variables, not how we calculate zeta and omega. So of course, here I got the same result. Yeah. Um, so it's still that flat line, which is very annoying. So I went back to what I did in the exam and yeah, just went over the steps again, but obviously that was not a problem. The like calculation or the steps of the for loop themselves were fine. The only thing that was not okay was the way I was calculating zeta and omega. So here I'm still checking that, and then probably around here, yeah, here I realized that MP and TP I was calculating differently in the for loop than in the other thing. Probably in the exam I looked at the workshop PDF and saw that they did it this way. But whilst I was recording this video, I was kind of tired and my roommate had just distracted me. So, yeah, I didn't think about checking the PDF, which is probably where I went wrong. So in the exam, you have access to those resources, so use them. Like that, you avoid making mistakes like this and having to like problem solve things that you shouldn't have to. So yeah, here I'm basically just correcting the code so that it matches what I did in the exam, um, which is basically in the question it said that we had to use the first peak, which is why I just changed TP to be the first entry of that list. Like that it's the first peak. And after changing that, I reran the thing and finally got a result. Hey, let's go. Um, so, okay, now that I know this works, we obviously still need to add the plot for the second simulation because this is only the small simulation. And I also wanted to add a bit of formatting because obviously each starting angle is separate, so having a continuous line doesn't make sense. So here I added the formatting wrong because I forgot that that has to be in like quotes, but here just copy paste all this to do the second plot. So like this, all you need to change is the title, obviously. And then also the variables. So here I'm checking what I actually named the variables and changing the names for the plot. And then here I remembered that they had to be within quotes. So star, obviously that is just like the little icon that it will use for the dots, and R is for red, so the zeta ones will be red instead of blue, and that just adds a little bit more distinction. It's not really necessary, but it looks better in my opinion, which is why I added it. So run the simulation one last time, and there we go. Hey, we got some nice looking plots. So yeah, um, that's basically it for questions A, B, C, D, I think. Um, and then E, F, and G, or D, E, F. I don't remember the naming anymore, honestly. But the other ones were just like analyzing the plots and making estimates. So I think that you should be able to do. Um, oh yeah, E, F, G, I guess. Um, But yeah, this is the bulk of what we had to know what to do, basically the two plots here, and then the two Simulink thingies here, and then the whole Matlab thing. But as you saw, the actual Simulink part is not that hard and very short. The stupid part is this whole Matlab thing. But yeah, I hope this helped, and good luck.